America can build the solar farm, it can install the battery park, it can finance the data center, approve the factory, and pour concrete for the next industrial boom. But none of it matters if one machine does not arrive. Not a chip, not a battery, not a solar panel. A transformer. Across the United States, energy projects are running into a bottleneck that most people never see. Solar farms can be ready before they can connect. Battery projects can sit waiting for substation equipment. Data centers can demand power faster than the grid can deliver it. Utilities are competing for the same heavy electrical hardware needed to keep the system reliable. This is not just a clean energy problem, it is a grid problem, an industrial strategy problem, and increasingly, a geopolitical problem. Because in the next phase of the energy race, the winner will not only be the country that builds the most generation, it will be the country that can connect it. The transformer is one of the least glamorous machines in the energy system. It does not generate electricity. It does not store electricity. It does not get the political attention that solar farms, nuclear reactors, or AI data centers receive. But without transformers, modern electricity cannot move. A project can be financed, permitted, and physically built. But if the right transformer does not arrive, it can sit there, electrically stranded. That is why transformer shortages are becoming one of the most important energy bottlenecks in America. For years, the clean energy conversation focused mostly on generation. How many gigawatts of solar America can build, how fast wind can scale, and how quickly batteries can turn daytime solar into evening power. Those questions still matter, but the deeper question is this: can the grid absorb all of this new power fast enough? In 2026, US developers plan a record amount of new utility-scale capacity, mostly from solar and battery storage. That sounds like progress, and in many ways it is, but every megawatt has to connect somewhere. Electricity is not useful just because it is generated. It becomes useful only when it can be moved, stepped up, stepped down, protected, balanced, and delivered to the places where people and machines actually need it. That is where transformers come in. At a power plant, a transformer steps voltage up so electricity can move over long distances efficiently. At substations, transformers adjust voltage as power moves through the transmission network. Near homes, factories, warehouses, and commercial districts, distribution transformers step voltage down again so electricity can be used safely. Every layer of the grid depends on them, and that is why this shortage hits America in such a strategic way. The United States is trying to expand almost every part of the electricity system at the same time. It is adding solar, batteries, data centers, EV charging, new factories, and grid upgrades, while also trying to maintain reliability through storms, heat waves, and rising peak demand. All of those sectors need transformers. A delayed transformer can delay a solar project, but it can also delay a battery project, a semiconductor plant, a new housing development, a grid hardening project, or an AI data center. In a normal supply chain shortage, one industry waits for one component. In this shortage, many parts of the American economy are competing for the same class of grid hardware. To understand why, we need to understand what a transformer actually does. A transformer changes voltage. That sounds simple, but it is one of the basic reasons the electric grid works at all. Power is stepped up to high voltage for efficient long-distance transmission, then stepped down again closer to the customer. A solar farm may generate electricity at one voltage, while the transmission grid operates at another. A generator step-up transformer makes that connection possible. Substation transformers move power between different levels of the grid. Distribution transformers reduce voltage to levels that can serve homes, offices, stores, warehouses, and industrial loads. So a transformer is not just another piece of electrical equipment. It is the interface between generation and the grid, between the grid and the customer, between industrial ambition and physical reality. And unlike many modern technologies, large transformers are not simple mass-market products. They are heavy industrial machines. They require specialized electrical steel, copper or aluminum windings, insulation systems, cooling systems, oil, tanks, bushings, testing, and engineering expertise. Many are built around specific voltage levels, utility standards, grid conditions, and project requirements. A solar panel can come off a high-volume production line. A battery cell can be manufactured in a gigafactory, but a large power transformer is closer to industrial equipment than consumer technology. It takes materials, skilled labor, factory capacity, logistics, and rigorous testing. That is why lead times can stretch from months into years. And that is why this shortage is difficult to solve quickly. You cannot fix it with an app. You cannot fix it by simply ordering more next month. Transformer production depends on physical manufacturing capacity. Electrical steel, copper, skilled workers, testing facilities, long planning cycles, and heavy transportation. This is the industrial side of the energy transition that often gets ignored. The public sees solar panels, wind turbines, EVs, and batteries. But the grid sees transformers, switchgear, substations, interconnection queues, protection systems, and crews. And right now, some of those less visible components are becoming the real bottlenecks. The conflict is simple. America wants to electrify faster than the grid supply chain can expand. Power demand is rising again after years of slower growth. AI data centers are creating large, concentrated loads. Industrial reshoring is increasing the need for reliable electrical infrastructure. Solar and battery projects are adding new capacity, but much of it requires new interconnection equipment. Utilities are replacing grid assets installed decades ago. All of this is happening at once, so who gets the transformer first? The utility replacing aging equipment? The solar developer waiting to connect a project? The battery storage site? The data center? The factory? The neighborhood that needs grid upgrades before new housing can be energized? This is not just a technical problem, it is an allocation problem. When transformer supply is tight, every project becomes part of a hidden competition for factory slots, materials, and delivery schedules. A developer may have financing, land, permits, equipment, construction crews, and a signed power contract. But if the transformer is delayed, the project can be delayed. And delays have consequences. Interest costs rise, construction schedules shift, power purchase agreements become harder to manage, interconnection timelines become uncertain. Developers order earlier, hold more inventory, and sometimes pay premiums to secure supply. Then the shortage feeds on itself. When buyers fear scarcity, they order earlier. Factory slots become more congested, lead times stretch, and everyone becomes more desperate to secure equipment ahead of schedule. That is how a bottleneck becomes a strategic constraint. In energy debates, people often ask whether America can build enough generation. But generation is only one layer. If a solar farm cannot connect, it does not matter how cheap the panels were. If a battery cannot interconnect, it cannot support the grid. If a factory cannot get reliable power, it cannot operate at full scale. If a data center cannot secure grid capacity, its servers do not matter. The electricity economy is only as strong as the infrastructure that connects it. And that brings us to the geopolitical layer. In the old energy world, geopolitical leverage often came from oil fields, pipelines, shipping lanes, and natural gas terminals. In the electrified economy, leverage increasingly comes from industrial capacity. Who can produce transformers? Who can supply high-voltage equipment? Who controls electrical steel? Who has the factories, workforce, and logistics to deliver grid hardware at scale? Who can connect new industrial load faster? This is where the energy transition becomes much more than a climate story. It becomes a manufacturing story, a supply chain story, and a national security story. If the United States depends too heavily on imported grid equipment, then its energy expansion is exposed to shipping delays, trade disputes, tariffs, material shortages, factory backlogs, and geopolitical tension. Even when suppliers are located in friendly countries, the basic problem remains. If global demand exceeds global production capacity, everyone is waiting in line. The transformer shortage shows that energy security in the 21st century is not just about fuel supply, it is also about equipment supply. A country can have natural gas, solar resources, wind corridors, and battery developers. But if it lacks the physical grid equipment to connect and move power, its energy advantage is limited. This matters especially for the United States, because the country is trying to decarbonize parts of its power system, power AI, rebuild domestic manufacturing, compete in clean technology, modernize an aging grid, and maintain reliability at the same time. That is a difficult industrial equation, and transformers sit inside that equation. The United States has world-class engineering, capital markets, utilities, software, and energy resources, but the question is whether its grid hardware supply chain can scale fast enough to match demand. This is not an argument against trade. America will still need trade. But strategic dependence is different from normal trade. If transformers remain a long-term constraint, then the pace of American electrification depends partly on foreign factories, global materials markets, and international logistics. That is not just an energy issue, that is industrial leverage. But there is an important nuance. Transformer shortages do not mean the energy transition is failing. They mean the energy transition is becoming real enough to stress the industrial system underneath it. When solar and batteries were smaller parts of the grid, their equipment needs were easier to absorb. But as they become major sources of new capacity, the hidden infrastructure becomes more important. A system-level transition always reveals bottlenecks. First, the bottleneck may be technology cost, then permitting, then interconnection, then transmission, then transformers, switchgear, workforce, and materials. The fact that transformers are now central to the story shows that renewable energy has moved from the edge of the grid into the industrial core of the power system. But it also means the conversation has to mature. It is not enough to say, build more clean energy. It is not enough to say, build more data centers. It is not enough to say, bring back manufacturing. All of those goals require grid capacity, and grid capacity requires physical equipment. There is also no single transformer shortage. Distribution transformers, large power transformers, substation transformers, and generator step-up transformers are different categories with different engineering and procurement challenges. That matters because solutions must be specific. Standardization can help reduce unnecessary variation. Better forecasting can give manufacturers confidence to expand capacity. Strategic reserves, refurbishment, grid-enhancing technologies, demand response, battery storage, and smarter interconnection planning can all reduce pressure, but none of these fully replace transformers. At some point, the physical grid still needs physical machines. This is the hard truth at the center of the story. You cannot software your way out of every hardware constraint. The energy transition is often described as digital, distributed, and intelligent. And that is partly true. Software will matter, AI forecasting will matter, advanced controls will matter, power electronics will matter. But electricity is still physical. It moves through copper and aluminum. It depends on steel, insulation, oil, substations, breakers, transformers, and crews. The more digital the economy becomes, the more it depends on the physical power system underneath it. That is the irony. AI may be one of the most advanced technologies in the economy, but an AI data center still needs transformers. A semiconductor fab may produce the chips of the future, but it still needs transformers. A battery plant may manufacture energy storage systems, but it still needs transformers. A solar farm may generate low-cost electricity, but it still needs transformers. The future is being built on machines that look old, heavy, and industrial. And that is exactly why they matter. So what should America take away from this? First, grid equipment has to be treated as strategic infrastructure, not just utility procurement. Transformers, switchgear, cables, and substations are the industrial foundation of electrification. Second, energy planning has to include supply chain realism. It is not enough to model how many gigawatts should be added. Planners also need to ask whether the equipment required to connect those gigawatts can actually be manufactured, delivered, installed, and maintained. Third, domestic manufacturing, standardization, and coordination matter. Not because America should make everything itself, but because a country that cannot produce enough critical grid equipment gives up control over the speed of its own electrification. And finally, the public conversation needs to shift. The energy transition is not only about what generates electricity, it is about what connects it. The next energy crisis may not look like an oil embargo or a gas shortage. It may look like a solar farm waiting for a transformer, a battery project waiting for a substation, a factory waiting for a grid upgrade, a data center waiting for high-voltage equipment, or a city waiting for replacement units after a storm. That kind of crisis is quieter. It does not always produce dramatic headlines, but it can slow the entire economy. Because electricity is becoming the operating system of modern civilization. And transformers are one of the machines that make that operating system work. In the next phase of the energy race, the winners will not simply be the countries that announce the biggest clean energy targets. They will be the countries that can build the grid hardware behind those targets. Because generation is not enough. Ambition is not enough. Capital is not enough. The power has to move. And in 2026, one of the most important questions in American energy is no longer just how much electricity the country can generate. It is how fast that electricity can be connected. That is why the transformer shortage matters. It is the quiet bottleneck behind solar, batteries, AI, manufacturing, and grid reliability. It is where the energy transition meets industrial reality. And it may become one of the defining infrastructure constraints of America's next decade. The most important machine in the energy race may not be the one that produces power. It may be the one that makes power usable. The transformer,